So let's try to find the answer to the question I posed. We took our matrix A and we partitioned it, and we then recognized that this is just the transpose of that because we chose to only store the lower triangular part of the matrix. This is a symmetric matrix in square, so is this, and then this becomes the transpose of that. Now, previously we took our matrix A and we partitioned it into a top part and a bottom part. All we really have done here is we're thinking of the top part as having a left part and a right part. So, if previously our loop invariant was that the top part had multiplied x and had been added to the top part of y, and the rest was left alone, the equivalent of that would be to say we've partitioned it like this and we've computed with these two pieces, and notice that that's the loop invariant where these two pieces are not part of it. The top part has finished, the bottom part has been left alone. Okay? Now similarly, we could say, what if we take our matrix A and partition it into a left part and a right part, which is what we did for loop invariant 3. And then we had to multiply that times x top, x bottom. Oh, here all we have done is said, oh, we'll think of the left part as having a top part and the bottom part and the right part as having a top part and a bottom part. And then the loop invariant was that currently y contained a left times x top plus the original contents of y. And the equivalent of that over here would be that these two terms go away, and you're left with these two terms being added to the original part of y. Okay, and that's how the two are related. Okay, now that we have answered that, we can think a little bit more generally. These are all the operations that have to be performed in order to update y top and y bottom. These are the original contents of y, so they have to be in the mix. We can't just go and get rid of those. But for each of these terms, we can choose to either have done them or not. Okay, so we could come up with a loop invariant where we've done everything except for that term, everything except for that term, everything except for these two terms, everything except for these two terms. If you think about it, some of them have to be there, some of them don't. But let's first systematically come up with all potential loop invariants, and then you can reason through those and say, some of them don't make sense. In what sense don't they make sense? For some of them, there's no loop guard that can be derived. And you can look at the loop invariant and the postcondition and say, this doesn't make sense. Or you can say, well, we can find the loop guard, but there is no initialization step that we can go through to put it in a state where the loop invariant is true. And with that, we can get rid of a bunch of them. And then we're actually left with the ones for which we can actually systematically derive algorithms. Okay, so how do we do that? Well, let me just sort of sketch out how we would go about it. One way to do it systematically is to create a table. You have the term a top left x top, a bottom left transpose x bottom, etc. We have 4 of these terms, right? And for each of them we can say, yes, it's in there, or no, it's not in there. Okay, and we can just enumerate them. How many different ways are there? Well, you have 4 choices. For each of them it's yes or no. That actually leads us to 16 potential loop invariants that we'll have to scrutinize to see whether they actually show some promise. Okay, so let me step out of the way, and there's the table.